right, to begin our algebra review this semester, I'm going to start with factoring as our first example. We'll go through a lot of different types of factoring, and in algebra it didn't seem like factoring had that much value to it. I mean, yeah, it was a nice little tool that helped us out, but in calculus, factoring can be very, very important. And the book is pretty nice in the fact that most of the problems that when you get into the calculus part, most of the problems will be factorable. And so if we can get this skill down, this will help us quite a bit when we get ready to get to the calculus part of the course. All right, first example, 2x squared plus 4x to the fifth minus 6x to the sixth. And the question is to factor this particular polynomial. Well, what's one of the things that can be factored out of here? Okay, definitely a 2, correct. Well, first we can look through all the numbers and see if there's any common factor that can be pulled out. In this case, we can take out a 2. And then we look at the variables. How many x's can be pulled out here? 2, right? We can take out an x squared. All right. Now we're looking for the rest of the factoring part. Okay. What we're doing is, it's almost like factoring is the opposite of the distributive property. We're trying to take and turn this back into a distributive property as opposed to having it in an expanded form. Okay. All right, now, what would I need to multiply this by so that I could end up with 2x squared? 1. Okay, so this turns into a 1. Then I put in the plus sign. What do I need to multiply this by so that I end up with 4x to the fifth? 2x cubed. And what about for the last term? 3x to the fourth. Correct. And so this is the correct factoring for this particular polynomial. So try to look for any numbers that can be factored out as well as any factors of x that can be pulled out. Okay, so this is a pretty easy example to start with. Okay. Now, there are some other types of factoring, such as this, x squared plus 5x plus 6. Okay. This is different than the first example because here we do not have any numbers that can be factored out, and we also don't have any x terms that can be factored out because this obviously is missing an x term. So we have to look at other ways of factoring. Well, another type of factoring, and this will be very common in the course, is to factor it into two binomials. Okay? Now, what needs to go in the front right here? X times x, sure. Okay? Because what we're trying to do on this example is we're trying to take what's commonly called the FOIL process. We're trying to undo that FOIL process. Okay? Now, some things that we'll be looking for when we try to decide what needs to go right here and right here, we need to look for two numbers that when they were multiplied together give me a 6, and that when we add the outside and the inside part of FOIL, that they give me a 5x. So can we think of two numbers that multiply to 6 and add up to 5? Well, 2 and 3, of course. So this is the correct factoring for this example. Now, if that was a little bit too fast, you don't remember this process, here's a way you can convince yourself that this is right. Go through and actually FOIL this binomial out. Okay? Multiply each term in the first binomial times each term in the second one. Go through and clean up all your like terms, and this is the answer that you should get. Okay? And so that's one thing that we are looking for, is being able to factor binomials. Let's just do another example of that one. X squared minus 7x plus 10. This was just a little different because I put a minus sign in here, but for the most part it's the same. Okay, we're looking for any factors here that may work. Okay, since it's x squared, x times x, and what are the numbers that we could use here? -2 and -5. Because those numbers would add up to -7, but if we multiply them together, they give us +10. And so this one also factors as well. Okay. All right, next example. 2x squared plus 6x minus 8. What may happen when we're doing factoring is we may get a little bit of this and then be able to do some factoring as we've done over here. Okay, and so that's what this example is referring to. First of all, what can I factor out according to this side? Okay, definitely I can take out a 2. Okay, doesn't look like I can take out an x because I don't have an x in this term here. Now, what do I have left after I factor out the 2? Okay, x squared, 3x minus 4. Sure, all I did for right now, I'm going to do this in 2 steps, I just factored out the 2. Okay. Now, once I have factored out the 2, now I want to look at this term and see, does it factor like we had over here? Okay. All right. Do you see any nice numbers that will work here? Okay. I think just the signs flip there. Yeah, I think if we do a positive 4, an x plus 4, and an x minus 1, this will work. Because if we multiply these together, we end up with negative 4. And if we do the outside and the inside part of FOIL, we've got a 4x and a negative 1x. That'll give me my positive 3x. And so yes, this is the correct factoring here. Okay. All right, another type of factoring is something called the difference of 2 squares. Okay? X squared minus 25. Okay? What's different about this one is that we are missing the term in the middle. We don't have any x to the first terms, any linear terms here. Okay? X squared minus 25 is called the difference of 2 squares because we have something squared right here and we also have something squared right here. Okay? What does this factor to? Probably somebody knows this. Yeah, x minus 5 times x plus 5. Sure. Okay? And what's really going on behind the scenes here is if I change this to x squared plus 0x minus 25, now this problem looks a lot like the one before. The only difference is we needed to get the outside and the inside, the FOIL parts, to add up to 0, and so that's why we had a plus 5 and a minus 5 so that they'd zero out. Okay? Be really careful with difference of 2 squares because if you get a problem that looks like this, x squared plus 16, okay, this one does not factor as a difference of 2 squares. Okay? You know, if we were guessing, okay, we might guess x plus 4 times x minus 4, but what happens when I take a positive times a negative? That's a negative number, but I need this to be a positive number, don't I? So if you have x squared plus 16, that's not the difference of 2 squares. That's why we can't factor it. Okay, so just making sure that the online people can see this, I want to cross this out that this is no good. Okay, the only time we can do a difference of 2 squares is when we have a subtraction sign here on the number. Right? So just be careful with those. In fact, this example up here, x squared plus 16, this one just does not factor. Okay, there's no factoring that we can do with it. Okay. Now, I want to tie factoring to the next, or one of the next things that we need to work with, and that is solving equations. Okay? This is why factoring will be so important for us, is that when we get to a certain spot in the course, we'll have, like, for example, this quadratic equation equal to 0. And we need to find out the solutions to this equation. So we go through and we factor, and we see that the factors are x plus 2 and x plus 3. And so now my question is, what if these are the factors, what are the solutions to the equation? Yeah, negative 2 is a solution, and negative 3 is a solution. Okay? Because if we sub in negative 2 into this factor, negative 2 plus 2 is 0. 0 times anything will give me 0. Okay? And similarly with the negative 3, that will also accomplish the same thing. Right? So in the course, a lot of times we will factor the quadratic, then we will get these solutions, and this will tell us something about the graph of the function. Okay? And that'll be the calculus part that I have to teach you later. Right? So what if we were doing this one down here? What if this one was equal to 0? What would be the solutions? 2 and 5, sure. All right? Okay. And similarly on the next 2 examples they would be the same, but maybe I should do this one here. Okay, this one's got something a little different on it. What are the solutions for this one? Definitely what comes out of here? Negative 4. Definitely out of here a 1. do I pick up any other solutions out of just a number that's out here? And the answer is no. Be really careful, because sometimes I'll get students that say, well, I think x equals 2 is also a solution, and that's not the correct answer here. Okay? Why is this not correct? Well, first of all, can 2 ever equal 0? Well, no, so that's one reason that this doesn't work. But the second reason is whenever you have a second degree equation, how many solutions can you have? You can only get 2 solutions. We've already got the 2 solutions here, so we can't pick up any extra solutions off of this. Okay? So any just numerical factors here don't produce any extra solutions. Only the ones that have x's in them produce solutions. Okay? Now I want to do one more example here with these equations here. What if I had you solve this equation? 3x cubed plus 12x squared plus 12x equal to 0. So say we're working along in a calculus problem, we get to this stage, we need to find out the solutions for x. Okay, what would you do first? Okay, definitely factor out a 3. And what else could be factored here? An x. Okay, so we'll go ahead and factor out an x at the same time. All right, what's left for the rest of my distributive property? Okay, x squared plus 4x plus 4. Sure. Okay. Now, the next thing that we try to do is we try to factor the quadratic. We try to factor the x squared term. Okay? And this one does factor. What are the 2 factors here? X plus 2 times another x plus 2. Okay? That will work in this case. Now, just to let you know how this would work out here, okay, what are my 3 solutions to this particular cubic equation? Well, definitely from here I get what? -2. From here I get another -2. I don't necessarily need to rewrite it again, although it does count as the second solution. It just happens to be the same one. And on this example, what solution do I get from here? I get 0, right? Okay. Because 3 times 0 definitely does give me 0. So any terms that have x's in them will produce solutions. This one didn't have an x in it, so that's why it didn't produce a solution. So even though this was a third degree equation, we only get 2 different solutions, even though, like I said, we really do have 3 solutions. It's just 2 of them happen to be the same number. Right? Okay, any questions with factoring or solving equations equal to 0? All right, very good. That's one thing that you'll see on your online quiz. The next major concept that we will look at here are what are called rational functions. We will have concepts later in the course that deal with something called a quotient rule, and so we will have division. Okay? And so I just need to review how do we add rational functions together and how do we multiply rational functions together. Again, because we will have a lot of this later on here. The example that I came up with, 1 over x plus 2 plus 2 over x minus 2. All right, so the first time we'll go through, we'll just add these together, and then here in a little bit we'll multiply them. All right? What do we need to be able to add 2 rational functions together? We need like terms, also called common denominator, right? Okay, so we need to have that. Now, what is my common denominator in this example? Okay, x plus 2 times x minus 2. In other words, what I am missing from this term is I'm missing the x minus 2 piece. Now, the thing is, in algebra, though, we can't just multiply by x minus 2 down here. What do I also need to do to keep this expression equivalent? Yes, I have to do the same thing up in the numerator. Okay? Because now it's almost like I'm multiplying by 1, because I'm multiplying by and dividing by the same thing. All right? Over here, I need to multiply by what? What's the missing piece of the denominator over here? The x plus 2 term, sure. And likewise up here in the numerator. Okay? The reason that we do this is now both terms have the same denominator, so we can now join them together as just one simple fraction. Okay? So x minus 2, x plus 2 in the denominator. And all we need to do now is just add the numerators together. Okay? Kind of like off to the side, if I told you to add 2/7 plus 3/7, okay, we just take the 7 and we let that be our denominator, exactly what we're doing here. And all we do is add 2 plus 3. We just add the numerator together to get 5/7. That's exactly what we're doing here. We're just adding these numerators together. Okay? So we've got x minus 2 just times 1, so I don't have to do anything because of multiplication by 1. Here, if I use the distributive property, I've got 2x plus 4. And then to finish off the problem, I'd want to go through and clean up the numerator here a little bit. So the denominator is still the same, and the numerator would be 3x plus 2, it looks like. Okay? And so this is how we add rational functions together. We get a common denominator, put all of our like terms together, we finish off the problem. Okay? Now, let's contrast that with what if I had you multiply these together? What if we were taking 1 over x plus 2 times 2 over x minus 2? Just multiply across, right? This is the much easier way to do. This is the much easier one than the addition, sure. Okay? All we need to do is multiply the numerators together to get a 2. All we need to do is multiply the denominators together to get x plus 2 times x minus 2. Okay? This is your answer, you're finished. Okay? So multiplication is very simple. We just multiply straight across. Okay? All right, questions with those rational functions? All right. The next concept that is related to rational functions is something called asymptotes. And one of the things that we spend a lot of time on in the calculus course is we spend a lot of time looking at graphs. And one of the features that shows up in a lot of graphs is we have different types of asymptotes. And we talked about these in college algebra, but I want to go ahead and review them because it's been a little while since you've seen them. All right. First type of asymptote that we'll look at is a vertical asymptote. Now, on a graph, a vertical asymptote would look something like this. You might have a graph that's coming along. It hits a point where there's no value, and then it continues on the other side. This would be a possible graph of what a vertical asymptote would look like. In equations, where do we get vertical asymptotes? Like, for example, let me rewrite it here. 1 over x plus 2 over x minus 2. If this was your equation, where do we get vertical asymptotes? And my clue is we want to look at the denominator, and the thing that we're looking for on a vertical asymptote is that we need the denominator to equal 0. If we can get the denominator to equal 0, that's where we have a problem on our graph. And you've heard this ever since 4th grade in division. We can never divide by 0. And so that's where the problem shows up on our graph. All right? What numbers would turn my denominators into 0? X equals negative 2 would turn this piece into 0. What about over here? Positive 2. Okay? So if I was to go through on my calculator and graph this equation, y equals this rational function, okay, I would see that at negative 2 I would not have a value, and I would see at positive 2 I would not have a value. So there would be 2 vertical asymptotes on this graph. Okay? And this will be important because later in the semester we'll talk about something called critical numbers, and one of the places we get critical numbers is from vertical asymptotes. Okay? So we've got to be able to identify vertical asymptotes. All right? Just when the denominator is equal to 0. The other type of asymptote that we will spend a lot of time on here next week already is something called a horizontal asymptote. And there's a lot of ways to approach a horizontal asymptote, but I'm going to approach it via the calculus way because that's what we're going to be talking about here shortly. Okay? A horizontal asymptote is as the x value gets really large, the y value equals what? Okay? That's what this is asking. A horizontal asymptote says as the x value gets really, really large, what happens to the y value? Okay? Let's do a specific example here. Okay? What if I give you this rational function, 2x over x plus 5? And we want to find the horizontal asymptote. In other words, we want to find out if I plug in really, really large numbers for x here, what does this fraction get really close to? Okay? And let's do this. We can do a little bit of roughing it here in our head. What if I plug in x equals 10? You know, not too big of a number, but what if I plug in x equals 10? My numerator is what? 20, and the denominator is 15. Okay? So 20 over 15, that's just a little bit bigger than 1. Okay? So 1 point something. All right, what if I plug in a bigger number? What if I plug in 100? Okay, the numerator is what? Numerator is 200. Denominator is what? 105. Okay? And again, just really roughing it here, what is this really close to? 200 divided by 105. Fairly close to 2, right, because 200 over 100 would be exactly 2, and we've got a little bit bigger denominator, so 1.9 something probably. Okay? What if I plug in 1,000? Numerator does what? Goes to 2,000, yes. Denominator is 1,005. And again, if I had you plug this in on your calculator, this number will be really close to 2 as well, but it will be even closer to 2 than this one was. Okay? And so this is the question that's being asked on the horizontal asymptote, is that if x gets really, really large, or if we could go all the way off to infinity, what would the y value be getting really, really close to? And in this particular problem, the answer is equal to 2. So whenever they talk about finding a horizontal asymptote, that's what it's asking for. As x gets really large, what's the y value get close to? Now, I did more work than you really need to do here. You don't have to plug in a small number like 10 or 100. You can just jump right in and plug in a really large number. Plug in 1,000,000 or something right away, and you'll get a pretty good idea what that horizontal asymptote is. Now, in college algebra, I teach horizontal asymptotes this way as well. Okay? And the fact that where does it look like this 2 is coming from? Back in our equation over here. Okay? Well, if we look at the strongest terms in the numerator and the denominator, of course, this is the strongest term up here because it's the only term, but this term is stronger down here because it is an x. And as the x's get bigger, this number gets really big. This number just stays the same. Okay? What's 2x divided by x? Well, that's 2. So if we divide the strongest terms by each other, that will tell us where this horizontal asymptote should be located. Okay? So that's a little trick that you can use if you want to work on a horizontal asymptote real quickly here. Okay? Another example of a horizontal asymptote. What if I give you this equation? We'll put an x in the numerator. We'll put x squared plus 2 in the denominator. All right, and again, we don't necessarily have to do all of these smaller numbers. Let's just plug in a fairly large number. I'll go ahead and let's just plug in 1,000 to start with. Okay, and a lot of times you might just do this on your calculator. You might just type in the number and see what it equals here. Okay, but in this particular fraction, our numerator is just 1,000 because it's just the value of x. The denominator is 1,000 squared plus 2. So that would be 1,000,000 plus 2. So 1,000,002. Now, what happens when we start to get really large numbers in the denominator? What happens when you divide by really big numbers? What happens to your quotient? gets really small, right? If I take 1 divided by 1,000, that's pretty small. If I take 1 divided by 1,000,000, that's even smaller. Okay? And so as our denominator gets really big, this value is getting even smaller. Okay? And so are there any guesses on what might happen if we keep putting in larger and larger numbers for x? It's going to get closer and closer to 0 this time, correct? Because my numbers are just going to get smaller and smaller, and as we get larger and larger here, this is just going to go towards 0. Okay? All right. Now, if we look at the strongest terms again, like I tried to do on this first example, x is the strongest term in the numerator, x squared is the strongest term in the denominator. Where is the strength? Well, the denominator is stronger, isn't it? If the denominator is stronger, your asymptote will always be going towards 0 because you'll always be dividing by a bigger number. So therefore, it always goes to 0. Okay? So that's another little clue. So here's two situations that we can have. If they have the same strength, this is x to the first, this is x to the first, then we'll approach whatever we get when we divide those two numbers. If the denominator is stronger, then we just go to 0 automatically. Okay? So there's a little bit of a review with horizontal asymptotes. We will do a lot more with these later, though, but this is what you need to know for right now. All right, last thing we'll cover here today is a little bit more with solving equations. And I'm going to start with a linear equation. 7x plus 4 equal to 3 minus 5x. And we want to solve this equation for x. Again, this will help us find certain things in calculus later as the course goes on here. All right, what would you do first if you were solving this equation? X is on the same side, and we can do that by adding 5x to both sides. Sure. And again, I'm going to show all the steps here for the review. You probably won't need to do this as you're working your own here. What would you do next? Okay, subtract 4 from both sides. So 12x is over here, negative 1 is over here, and then finally we do what? Divide off the 12. So the initial step, or steps, is to put all of your terms together. All the x terms need to be joined together. All of the numbers need to be joined together. And then when you get to the last step, you can do a division to finish off the problem here. So x equals negative 1/12 on this example. Okay? So linear equations, fairly simple here. Okay? What if we're working a rational equation? 1 over x plus 2, 2 over x minus 2 equals 0. So the one that I had before is a rational equation. And we want to solve this. Okay, how do we solve this particular equation? Well, probably the first thing to do is what we did earlier, is to join these two together as one single fraction. Okay? And just to save some time here, we should already have this in our notes. The common denominator was x plus 2 times x minus 2. What did we have in the numerator? I forgot. When we combined these together, what did we get for the numerator? 3x plus 2? Okay, thank you. So 3x plus 2 is our numerator, and this gets set equal to 0. Now, when we have rational functions that are equal to 0, okay, there's a little shortcut that we can use. Okay? Think about it this way. If I've got something divided by something that needs to equal 0, okay, which one of these two needs to be the 0? Does the A need to be 0 or does the B? Think back to just basic division problems. Which one is equal to 0? Is 7 divided by 0 equal to 0 or is 0 divided by 7? Which one of those is the one that equals 0? The second one, right. This is the one that equals 0. Okay, so again, I'll cross this off. Right? So when we're doing solving of equations with rational functions, the only piece that we really need to worry about is we need to make sure that the numerator turns into 0. Right? So I can ignore this and this as factors. I don't have to worry about those because I don't care what that number is. This could easily be a 5 and I would still get an answer of 0 down here. So I ignore the denominator, and the only thing I have to do is set this numerator equal to 0. And now this problem is a lot like the one we just solved. Subtract 2 from both sides, divide by 3, and so x equals negative 2/3 is the only solution to this problem. Okay? Now, 2 and negative 2, what were both of those from earlier? When the denominator equals 0, what did we call those a little bit ago? Right? Those were the vertical asymptotes, not the horizontal, but the vertical asymptotes from before. That's when the denominator is equal to 0, but when we solve the equation, we just need to worry about the numerator equal to 0. Okay? So this is the only solution to this problem is negative 2/3. All right? Let's do another example here. So what if we have a situation like this? I just told you that the only thing that matters is that we need the numerator to equal 0, but can this numerator equal 0? Can 2 equal 0? The answer is no. So right away, without doing any calculation on this, we can say that there is no solution to this problem. Okay? We cannot, there's no matter what number I want to sub in here for x, I will never get this fraction to turn into 0. And the reason is because the numerator is a fixed 2. There's no way I can ever get that numerator to turn into a value of 0. Okay? And that will also happen this semester. There will be problems where there's a solution, and again, that will tell us something about the graph of the equation when we get no solution. Okay? All right? So this is another possibility. And then let's look at this one right here. Whoops. 5x squared equals negative 7x. So what if we work through a problem and we get down to this point right here? Okay? How do we want to solve this for x? Okay? Well, notice what I've been doing on all my examples so far. I've been trying to get things equal to 0 on these rational equations. And so what should I do first on this one? Probably add the 7x over. Let's get things equal to 0. Because that's when we can do things like factoring, is when we have stuff equal to 0. All right, so what do we get when we factor out of here? What could be factored out? I can definitely take out an x, because I have at least one of them in both terms here. What is left from the first term? 5x, and from the second term I have a 7, correct. So 5x plus 7. What's the solution then for this factor? 0. And what's the solution for this factor? Okay, well, it's not a nice number like all the ones we've had earlier today, but all we've got to do is just kind of off to the side, set that factor equal to 0, and then do our little algebra and solve it. Okay, so if I subtract 7 from both sides, and then divide by 5, it looks like the other solution would be negative 7 over 5. And so these would be my two solutions for this particular rational equation. Okay. Questions? All right. We'll see you then here in a couple days. And if you want to start the algebra review quiz, you are more than welcome to do so.